please.
Okay, let's start. Today's talk is about well-poised hypersurfaces, and I will follow the work of these authors. So my plan for today is to start with main results of the paper. After that, I will give a construction of a tropical hypersurface. And in the end, I would like to give a few words about tropical geometry in some abstract sense. So let's start. First, let me give some notations and definitions. Let K of X be the polynomial ring in n variables over an algebraically closed field K. And let me consider a polynomial in such form. Here I will denote monomials as bold x in the degree of bold a sub I. So a sub I is the exponent vector. And now let me define an initial form of the polynomial. For any vector omega, I can define the initial form of polynomial f. It is the sum of all terms such that the inner product of exponent vector of this term with omega is maximal.
It is good to imagine here the Newton polytope of this.
Yes, and also I have an example. So, for example, if omega is vector a and 2, initial form of this polynomial will be such polynomial in cases, in angles. The maximal inner product will be 4 plus 8, 12. And also, I will consider the initial ideal. It is the ideal generated by all initial forms. So in my example, ideal was principal. So initial ideal is just ideal generated by one initial form. Okay, stop me if it will be something unclear. Yeah, I will go further then. And now I will define a well-poised polynomial. So the topic of my talk is well-poised hypersurfaces. It is logically to define a well-poised polynomial. Polynomial is said to be well-poised if every initial form, which is not a monomial, is irreducible.
And can you translate into Russian, well-poised?
Хорошо устроенный.
No. Okay, this will be a task for you. Please translate it after the talk. Okay.
Okay, and some more conventions. The great common divisor of two exponent vectors, a sub I and a sub j, is the great common divisor of all entries of these two exponent vectors. In other words, it is a maximal possible d such that a sub I is d multiplied by some other exponent vectors, and a sub j is d multiplied by some other exponent vector as well. This is we will need for some technicals, lemmas and so on. And also I will recall the support of a monomial. I will denote it by support sub of x in the degree of a sub I. It is a set of such indices that coordinates of exponent vector isn't 0. So if we have relative variable in our monomial, then relative index is in our support. And also it is logically to define such polynomial. A polynomial is said to be disjointly supported if the intersection of any two supports of its monomials is empty set.
So if they don't have common terms?
Yes. No, not. not common terms, but if any variable is only in one monomial, only.
I see.
Every two monomials are k-prime.
I see.
Mhm.
Mhm, mhm.
So, and now I'm ready to give you main results of this paper. Theorem 1 states that a polynomial f is well poised if and only if f is disjointly supported, and also great common divisors of any pair of two exponents in it equals to 1. So authors give a complete description of such polynomials. And also they give complete description of combinatorial invariance of these polynomials and the hypersurfaces. Theorem 2 states that if we have well-poised polynomial, then first of all, its Newton polytope is a simplex. And moreover, these Newton polytopes have no lattice points, have no lattice points, only vertex set is a lattice points in F, in N of F.
Viktoria, once more, polynomial is disjointly supported if any two terms depends on different variables, right?
Yes.
Mm-hmm. And what about well-poised? Let us look again to the definition.
A polynomial is said to be well-poised if every initial form, which is not a monomial, is irreducible.
Mm-hmm. Mm-hmm. So this is some sum of monomials, and it should be not a product of some two other polynomials. And question, if you have a polynomial which consists of monomials which are disjointly supported, can it be reducible?
Yes, it can be. I think x square minus y square.
Sure. X square minus y square. Okay, okay, clear. And this is why we have this condition that some greatest common divisor should be 1, something like this.
Yeah. Yes.
And what is the definition of Newton polytope? Because there are variants. Do we include?
I will give it a bit later, but it is usual definition, as you know. So we should point exponent vectors in the space and take a convex hull of these points.
Without origin. Sometimes origin is added. Okay.
It should be strange because the origin corresponds to a constant term, right? So constant term may be appearing in the polynomial or not. So it's strange to require by definition that the origin is included, right?
But it's very useful to consider such Newton polynomials.
Okay.
I have a definition without this statement about origin, but when I will construct a tropical variety, I will consider a polynomial without constant term. So my Newton polytope will be in such way. Here everybody understands the main results. I can. Yes, okay.
In fact, as such a formulation, let us return to theorem 1 and theorem 2. They looks like a simple lemma, something like this, because it's not clear why we should consider polynomials such that any initial term, if it is not monomial, then it is irreducible, and such a quite predictable characterization. So
yes, and the proof is quite simple, so I will prove these facts completely.
Mm-hmm.
Okay, let me start. I start with the description of Newton polytope and some supporting lemmas. The Newton polytope of a polynomial is a convex hull of the set of its exponent vectors. And first, notice that each face of Newton polytope has the form Newton polytope of some initial form of our polynomial f. Here I should remind that initial form, it is a subsum of our polynomial where inner product of omega with exponent vectors in this initial form is maximal. So it is very logical to notice. And also reminds that if f is a reducible polynomial, then its Newton polytope is Minkowski sum of Newton polytopes of its divisors. So the first lemma, if f is well-poised polynomial, then all monomials corresponding to the vertices of Newton polytope of f have disjoint supports. Let me prove this. Consider some variable in f and consider the set of those exponent vectors. Firstly, this exponent vectors should be a vertex of our Newton polytope. And secondly, let J belong to a support of associated monomial. And we will prove that S has only one element. So let me choose an element from S, A overlined, such that inner product of it with basis vector is maximal. In other words, our variable is in associated monomial in the maximal possible degree. And then this vertex is the only element in S. Indeed, since any face of our Newton polytope corresponds to an initial form, no vertices in S may share an edge, because this would correspond to a factorable initial binomial form of f. We just can factor out the lower power of our x sub j. And if we suppose there is some other vertex in the set, we will give a contradiction, because if these two vertices are unjoined by some ray, then the polytope isn't convex, because this set is the set of vertices of our Newton polytope. And otherwise, we will obtain an edge which corresponds to a reducible initial form. So can I go further?
Okay.
Yes, yeah. Lemma 2, if the monomials corresponding to the vertices of Newton polytope have disjoint supports, then our Newton polytope is a simplex. It is simple to understand because since the monomials have disjoint supports, the corresponding vertices in our Newton polytope are finally independent. So Newton polytope is the convex hull of a finally independent set of points, in other words, simplex, that's all. And then also I have two lemmas a bit technical, so I decided not to give a full proof of these lemmas, because we can, it can be a bit messy because of a lot of indices and so on. So let f be a polynomial such that the vertices of Newton polytope have disjoint supports. And if also f has great common divisor equals to 1 for all pairs of vertices a sub I and a sub j, then Newton polytope contains no lattice points besides its vertices. And also I have lemma 4, a binomial is irreducible if and only if it is disjointly supported, and also great common divisor of its exponent vectors equals to 1. And what about lemma 4? I will give an idea of proof. So we can prove sufficiency. Notice that Newton polytope of a binomial is a line segment. And suppose that our binomial is reducible. Then we know that Newton polytope decomposes into Minkowski sum of Newton polytopes of its divisors. Consider Newton polytope of Q. It can be a line segment or a point only because of dimensions. And if Newton polytope of Q is a point different from origin, then F can't have disjoint supports because therefore Q is a monomial which was factored out from F. But if Newton polytope of Q is a line segment, then Minkowski sum contains an entire lattice points. But our F satisfies to lemma 3, which states that F can doesn't have any interior lattice point. So last variant, the Newton polytope of Q can be only the origin, and it means that Q is a constant. And necessity. If F is reducible, then it is obvious that our monomials from it must have disjoint supports, because if they didn't, we could factor out a power of some variable. But if we suppose that great common divisor of two exponent vectors is d greater than 1, we can see that F is factorable. Factorable in article autos gives factorization of F. But it isn't difficult, but I decided not to give it here. And that's all. Now I'm ready to prove main theorems, but I will start with the theorem 2. I will remind it, let F be well-poised, then Newton polytope is a simplex. And moreover, Newton polytope intersect with lattice is precisely the vertex set of Newton polytope. And the proof. If we have that F is well-poised, then by lemma 1, the vertices have disjoint supports. Then we can apply lemma 2 and obtain that Newton polytope is a simplex. And since Newton polytope is a simplex, that for any two vertices, there is some edge connecting them to the reducible initial form. And then we can apply lemma 4 and obtain then any pair of vertices have great common divisor equals to 1. So after all, we apply lemma 3 and conclude there are no interior lattice points in our Newton polytope. And also theorem 1, I will remind it as well, a polynomial is well-poised if and only if F is disjointly supported and the great common divisor of any two pairs of exponent vectors in it equals to 1. Proof of the necessity is very similar to previous theorem, because in previous theorem we have already proved that if F is well-poised, then he is disjointly supported. And any two exponent vectors have great common divisor equals to 1. So we need to prove only sufficiency. By lemma 2, we have that Newton polytope is a simplex. Now consider an arbitrary initial form and suppose that it is reducible. Then we can decompose Newton polytope of this initial form into the sum of two Newton polytopes. Recall that Newton polytope of F is a simplex. Therefore, Newton polytope of initial form is a simplex as well, because it is just a face of our Newton polytope of F. And any Minkowski decomposition of a simplex is the sum of a point and the simplex. So this point cannot be a point different from origin, because in this way we can factor out some degree of some variable. So by the disjoint supports condition, we have that this point just must be the origin. So one of the G sub 1 or G sub 2 should be a constant. And now we will construct another combinatorial invariant of this hypersurface, a tropical variety. I will give this definition. The tropical variety associated to an ideal E is the set of such vectors whose associated ideal of initial forms contains no monomials. And let me consider
and
F.
ideal, it is in the polynomial algebra.
Yes. And let me consider a polynomial F, a disjointly supported polynomial with no constant term. I need one more definition. A polynomial is said to be omega homogeneous if its initial form associated to omega equals to F precisely. Or equivalently, every inner product of omega with exponent vector in F is the same for all I. If we consider omega the vector of all units, it will be the usual for us homogeneous polynomial. And now let me consider L sub f, the homogeneity space of polynomial f. So it's just such vectors in a product with which is the same for all indices. And for each exponent, I will define the vector wi. It is the vector with entry 0 for those indices that doesn't belong to support of this exponent, and -1 for those indexes that belongs to support of this exponent. Now let us notice that this homogeneity space isn't empty. If we consider vector of all units, then such inner product of this vector with some exponent vector, which I denote by L sub I, is always positive, and it is just a simple sum of all coordinates of this exponent vector. Now I will consider least common multiple of all of these inner products, and I will take the vector v sub f with entry L divided by L sub I at any index in support is A sub I, and L divided by L sub j at any index in support A sub j, and so on. So I recall that our polynomial is disjointly supported, so I can do this. And then we can check that inner product of this vector with all our exponents is the same. I can give a precise, simple example if you need. I have it. Okay, Yulia agrees.
It seems that we can understand it geometrically. We should take the plane which contains all the points, and just to take a normal vector.
but this normal vector will be 0 with all these points. But in a
this
product,
plane is not contain, doesn't contain origin because of this argument with positivity of vectors with all ones.
And why do they belong to one hyperplane?
Okay.
Yulia, can you repeat, please?
I haven't understood why all the points belong to some plane or hyperplane. Maybe I missed what Sergei Alexandrovich said. Sorry.
Okay, it's not very obvious, but okay.
I don't understand why we should take take a normal vector, because I have the same inner products, but it isn't equals to 0 now. So I can give a small example. If we consider a polynomial f, x plus squared y plus zw, it is disjointly supported, and we have such exponent vectors a1 1 0 0 0, a2 0 2 0 0, and a3 0 0 1 1. So we can notice that L sub 1 is 0. It's just the sum of all coordinates. L sub 2 is 2. L sub 3 is 2 as well. And L is the least common multiple is 2 as well. So what about vector v sub f? We will put on the place 1 2 divided by L1, because the place 1 is the support of the A1. We will make the second coordinate 1, because it is the support of the exponent A2. And so we need to divide our L to L sub 2, and we obtain 1. And also, two other coordinates is the support of our exponent A3. So we will place L divided by L3 here, 1 and 1. Yulia, it is clear? So, okay, we'll return to the slide. This vector is in our homogeneity space of polynomial. The first proposition, consider that S is any subset of numbers from 1 to k, and consider associated polynomial f sub S is subsum of associated monomials. And also let C sub S be such vectors omega, such that associated to omega in an initial form equals to F sub S. Then we can obtain a great result. We can obtain the construction, the full construction of this C sub S. It's just our homogeneity space plus such cone generated by vectors W sub I, which I determined earlier. And also notice that by definition, the tropical variety is the union of such C sub S, where our set S has at least 2 elements, because tropical variety is such union of vectors that has initial forms without any monomials. And I will prove it now. I will prove this equity just by inclusion in both sides.
And
So,
I'm sorry, maybe I lost something. Do you have examples of tropical varieties in this sense?
I have examples of tropical variety by other definition. So,
So you need another definition, and then you will get.
Yes. I will do some simple example of tropical geometry, and there is some connection, some very obvious connection, but I don't prove it. Okay, consider now the vector omega is in our the right side of our equity. So omega belongs to homogeneity space plus this cone. And consider associated initial form to omega. Also, we can assume that omega is just the sum of wi with positive coefficients, because in LF there are only those vectors which save the polynomial with when we consider initial forms. So in LF there are some vectors associated in initial forms to Z is just our polynomial f. And as our polynomial has disjoint supports, we have that omega with all exponents with indices in our set is 0. And omega with all exponents, all other exponents is less than 0. Here I should recall the definition of this vector W sub I. We have zeros in those indices that doesn't belong to S, and minus ones in others, in that belongs to S. And this means that initial form associated to omega is precisely our F sub S, because with elements from S, inner product is maximal. So we have proved the inclusion in this side. In another side, consider now omega belongs to C sub S. Then omega should be k, some k for all exponent vectors from S. And let me denote k sub j, all others inner products, which is not the same for indices that doesn't belong to S. First, notice that this kj is less than k, because C sub S is the set of those omegas such that initial form equals to F sub S. So K should be maximal of inner product. And then consider such vector from omega. We will subtract such sum. First of all, notice that k is greater than k sub j, so this coefficient is positive. And also one can check that this vector weights all monomials of f equally. So this vector belongs to our homogeneity space. And then we obtain that omega, that's why belongs to homogeneity space plus sum of W sub I. And we obtain inclusion to another side. A bit more technical proof. Okay, so what we obtain? We have that now we understand that C sub S is the sum of homogeneity space and such cone. And we understand what are the generators of this cone. If we understand what is the basis of homogeneity space, everything will be clear. We completely construct the structure of our tropical variety. So let me find the basis of the homogeneity space. Firstly, recall that we have our vector V sub f from this homogeneity space. And also note that we can choose any lambda from the homogeneity space, and there will be some q such that this equity satisfies lambda minus q multiplied by vector V sub f with any exponent vector equals to 0. So if we obtain the basis of the space n sub f of such lambdas, which gives 0 with all exponent vectors, then we will obtain the basis of our homogeneity space. And for a basis of this space, we will take such vectors. Can I draw something? I will explain. If we have some exponent vector, for example, zeros, a1, and there is some ag, we will take the vector v in this way: zeros minus aj and a1 in the place of j. So I need this for the operation that if I consider in a product of two these vectors, it will be 0. Because everything is vanishes. And if I consider in a product with some other exponent vector, it will be 0 as well, because our polynomial have disjoint supports. So all these vectors construct the basis of our space n sub f, and we should add only our vector v sub f to construct the basis of our space L sub f. In the example, in this example, we have only one non-zero vector of this v sub ij. This is vector v sub 2, 3. It looks like this. So, for example, if we consider our set S is the set of 1 and 2, we will need to take such basis. We will need to take v sub f, v sub 2 and 3, and also we have only one w sub I. It is the vector 0, 0, minus 1, minus 1, because we should to take zeros in the indices that belongs to our S, and minus ones in the indices which doesn't belong to our set. So, and now I can say a few words about tropical geometry, and it is the end of my talk, honestly. So what about the tropical geometry? We can define even a tropical semi-ring. We should take a simple R and add minus infinity to it, and consider such two operations. The tropical sum of two numbers is their maximum in our normal sense, and the tropical product is the usual sum of two numbers. And notice that both operations are associative and commutative compositions, and moreover, the distributive law holds, and also we have the additive neutral element. It's a minus infinity. That's why we need to add it. So we can consider polynomials in this semi-ring. For example, we can consider such polynomial. It is the polynomial minus x squared plus x plus 2. In our usual sense, it is just a maximum of such three linear functions. And we can even draw the graph of this function. It looks like a piecewise linear function. And also notice that we can define a zero set of any polynomial. It isn't interesting to consider such points where our polynomial equals to minus infinity, because there are a few such cases. That's why I will define zero set in such way. Let f be a tropical polynomial. A point is a zero of this polynomial if the value is attained in this point at least two terms of this polynomial. Or another definition that our function isn't differentiable in these points. So in this picture, I can say that there is two zeros. This is 1 and 2. This corners of my graph is associated to zero set of the polynomial. This is the end of my presentation and everything that I would like to say. This is the pure sense of tropical geometry. We can consider tropical semi-ring and consider polynomials in this semi-ring and their zero sets. Our first definition is equivalent. And there are some definitions, as I understood, as well. Some definitions with the help of series, for example. That's all.
No, Victoria, but what is the connection between this last classical tropical geometry and what was said before?
I can't prove it precisely because, first of all, I have found only big materials about tropical varieties. In the article was only the first definition. But as I understood, we can intuitively understand this is in some way because we consider initial forms associated to vectors, and tropical variety is the set of such vectors where initial forms has no monomials. We define initial form by taking sum and maximum because we make inner products. The condition that this initial form has no monomials can mean that the value of polynomial in this point is attained at least two terms. So when initial form has the form of monomial, it means that our maximum becomes only one time. And when our initial form has no monomials, it means that at least two terms has the maximum of inner product.
It's not completely clear for me, but can you return to formulations of theorem 1 and theorem 2?
Theorem 1.
You had slide with both theorems. Here it is. So now it's stated without any tropical geometry, right? So everything is defined, what is well-posed, what is degenerately ported, what is GCD. So this is some quite elementary purely algebraic results. But can you formulate these theorems in some tropical way? Maybe we can do the following. Do you have a file with the paper? Can you put it on the screen?
Yes, of course. 1 minute.
So how the author formulates the result in the abstract, say?
Yes, that is. So they say that an ideal is said to be well-poised if all of the initial ideas obtained from points in the tropical variety are prime. So tropical variety, like Newton polytope, is just a construction which helps to describe our normal, not normal, but our usual variety, as I understood. And people consider this well-poised initials not only principal, and there are some amount of articles in this topic as well. And what about this paper? They say something about tropical geometry in introduction. So, for example, they say that I would like to say something that they have example of Newton-Okounkov body. So, for example, if our variety, as I understood, is well-poised, so enough good variety, it is possible to show that each prime cone in our tropical variety is associated to a Newton-Okounkov body.
But okay, without this body, maybe look at the abstract.
Abstract is here.
Okay. So the claim is that we classify all principal ideals, or in other terms, all hypersurfaces, which have this well-poised property. So initial ideal obtains from the points in the tropical variety. So initial ideals which correspond to non-monomial leading terms, right? Initial terms. They are prime. And in your presentation, this prime was replaced by what?
Every initial form irreducible.
And what is the relation? Why it is the same as to be prime? Because this is a principal ideal, right? And principal
yes, because it is so Yes, yes.
Principal ideals is prime if and only if the generator is a reducer. So I see that. So the original tropical point of interest was that this condition, that the variety corresponding to points in tropical varieties, the ideals in the corresponding to points in tropical varieties, they are prime. And here we consider the particular case when we have a principal idea. Okay, I see. Maybe some other questions, comments? For me, it was interesting because I met many times this well-poised in some papers which I obtained in this or in that way, and I was interested to understand what is this. But this motivation which comes from tropical geometry, at least for me, is not clear. So maybe we should study it in more details. What is a connection?
And I have a question. You asked me about the name of the paper in Russian. So do you know how to translate well-poised?
Удачно сбалансированный, по-моему. Please use translator. This is one point. One moment.
Sorry, I have every time I have this test.
Okay, because you are doing something strange.
Many robots.
It seems to be very strange. Хорошо уравновешенный.
Let me try. Well-poised.
Maybe if you put a dash there, well-poised with the dash, then it will be just one word.
I have a translation хорошо уравновешенный when I put to Yandex. Okay.
Уравновешенный.
So this understanding why it is well-poised in this sense, or maybe it's not very clear from this paper. Okay, it was just.
Am I right that it is an open condition that if I take, how to say in English, случайный?
Random?
What? I'm sorry.
Arbitrary or some.
Arbitrary polynomial, it should be well.
Let us use English correctly. Arbitrary, this is произвольный. If you want to be случайный, this is random.
Okay, random polynomial. Am I right that random polynomial is with surely be well-poised or not? It should not be with prime monomials, yes?
Yeah, I don't know what is random. Maybe with some probability you will get.
This is not a question of probabilities. This is purely algebraic question. We have that some condition is fulfilled in a general position if the set of points where we have this condition is open and dense. So this is a generic property. We don't compute probability. So is it true that if you consider all polynomials of a fixed degree, this is some finite dimensional vector space, and polynomial is a point in this space because it is given by a collection of coefficients. So we are interested in some properties which are fulfilled for an open dense subset in this space.
We have a problem here because the problem is to define the space itself. It's infinite dimensional.
No, but we restrict we may restrict degrees of polynomials.
It depends on how you restrict, maybe. But
maybe, but if the answer to Sergei's question is yes, then it should be for, say, I don't know, quite big degrees. If you restrict by degrees by some big number, then it should be open condition. Something like this.
If you take a random polynomial like that, then you have polynomial with non-zero coefficients for each monomial, I guess. So it's
yes, you're right, of course.
It's Newton polynomial is filled. with its monomials?
Not field, but
Well,
this is a simplex.
no.
If I divide it by some diagonal, you're right that this depends on how we cut our exponential vectors. But if you cut by diagonal, then it should be simplex.
Yes, but if a lot of points are inside the
A lot of points. Okay.
polytope, then probably it should be bad. I don't know.
It seems that it is bad. Okay. So it's close condition, not open.
Okay, any more questions, comments? If not, then let us consider this talk as a short New Year approximation to tropical geometry. So maybe later we will go deeper in this subject and we will discuss in more details, because the paper looks to be understandable. Some points are quite elementary, and my idea was just to define some notions from tropical geometry. And this well-poised now is really popular notion through several papers. But at the moment, I don't see good motivation for us to deal with this notion. Okay, so if no more questions, no more comments, many thanks to Viktoria for her presentation.